We will continue our understanding of the derivative by looking at what we will call an inflection point. Recall that we were able to measure the concavity of a function f of x by looking at its second derivative. We found that f of x is concave down if its second derivative is negative, and f of x is concave up if its second derivative is positive. Let's now visualize this by looking at the graphs of f of x, f prime of x, and f double prime of x. Notice on the left-hand side of the graph of f of x, the function is concave down. Remember that our first definition of concave down was that a function is concave down if its rate of change is decreasing. Which is why if we look at the graph of f prime of x, the purple region is decreasing. Finally, since f prime of x is decreasing, that means its derivative, which is the second derivative of f, is negative. So the region where f of x is concave down is the region where f double prime of x is negative, which we can see on our graph of f double prime. Similarly, on the right-hand side, the graph of f of x is concave up. This is because our rates of change, or derivative, is increasing, which means that the second derivative is positive. Let's now make some further observations. The first is that if f double prime of x is going to change from negative to positive, as it does here, or similarly from positive to negative, there must be a point where f double prime of x equals 0. In other words, we can't change from negative to positive or positive to negative without crossing through 0. What effect does this have on the graph of f of x? Notice that as the second derivative changes from negative to positive, the original graph f of x changes from concave down to concave up. In other words, whenever the second derivative changes sign, the original function changes concavity. The last observation I want to make is what role does this point play in the graph of f prime of x? Notice, if f double prime of x is 0, that means it's a critical point for f prime of x. Furthermore, f double prime changes from negative to positive, which means that it's a local min for the graph f prime of x. Similarly, if f double prime of x changed from positive to negative, then we would have a local max for f prime of x. These observations lead to our definition of an inflection point. We say that if f of x changes concavity at x equals c, that is, it changes from concave up to concave down, or concave down to concave up, then we call x equals c an inflection point of f of x. What we just saw, that is, if f of x changes from concave up to concave down, or vice versa, that f double prime changes from negative to positive, which means that f double prime must pass through 0. So we have that if x equals c is an inflection point of f of x, then the second derivative, f double prime of c, equals 0. This gives us an algebraic way to find inflection points. We do have to be careful though. We can have a point where f double prime at d equals 0 for some value x equals d, that is not an inflection point. This is similar to when we had critical points that are neither local max nor local min. Let's now incorporate our last observation. We saw that if f double prime of x changes from negative to positive or positive to negative, that f prime of x must have a local max or local min. This means that at an inflection point, since f prime must have a local max or local min, that f of x has a point of greatest decrease or a point of greatest increase. Let's now look at this idea graphically. In the case where f of x has an inflection point and we change from concave down to concave up, then f of x has a point of greatest decrease. That is, f of x is decreasing most rapidly at the inflection point. In other words, f of x has its steepest slope down. On the other hand, if f of x changes from concave up to concave down, then f of x has a point of greatest increase. That is, f of x has its steepest slope up. Let's use what we just found to look at an example. Let's find when the function f of x equals x cubed minus 3x squared plus 3x plus 6 is concave up. To figure out when a function is concave up, what we need to do is find when the second derivative is positive. So let's start by finding the second derivative. To do this, we'll compute that the first derivative, f prime of x, is 3x squared minus 6x plus 3, and the second derivative, f double prime of x, is 6x minus 6. So to find when our function is concave up, we need to know when is 6x minus 6 greater than 0. To solve this inequality, we need to add 6 to both sides to get that 6x must be greater than 6, and so x must be greater than 1. So our conclusion is that f of x is concave up when x is greater than 1.